Un, 2, un. Un, un, 2, un. Hello.
agora... ok. Está mesmo.
Foi mais ou nada.
Are you good?
And that's, yeah. You had the next time.
Close my stuff.
Eu nem quero usar isto. Isto vai para o certo. Não tens o Chrome que é para poder usar a Argentex.
Yeah. Also, by the way. Argentex. Yeah, same.
Temporário por causa da password disto.
Naps.
Também
There's no money there, so.
Cool.
check. I mean, my laptop is over there, so but probably missing some small detail that I. Oh yeah. Oh, you were missing the built-ins there. Yeah, that's what I was missing. Okay. Tá, o quê? Tá.
Good morning. My name is Gilles. I'm an engineering at Lightshift Capital. Just an heads up before we start this. We cannot eat or drink anything in this room, right? And if you need some power outlets, or you can find them at that corner.
Thank you.
So the idea here in this repo is not just to learn these StarkNet and Cairo. Is for you to be able to always also use it on the hackathon. Start building your own application. So we put it like a small React application. Actually, it's the Next.js application for you to be able to see our examples and to build your own. So I will just give a brief explanation of the structure and stuff like that for you to be able to use it if you want on the hackathon itself. Unfortunately, we could not be able to use it with the DevNet, but you can use it on testnet. So yeah, it's working with that. So let's see. The main packages that we are using here are the StarkNet.js itself. Like it's a bit hard with only one hand. I'm sorry. It's this one, and on top of that, we are using this one as well, the StarkNet React Core, because this provides a set of hooks, React hooks. It's easier to use and it integrates with the Argentext wallet pretty well. It's a good package. This is, as I said, this is a Next application. Next is like a framework built with on top of React or something like that. So it's basically a React application. So we have this structure here. As you can see inside the package, the web, we have this file structure. You can start by looking at pages. You have inside that like the entry point of the application, this one. On here, we build like a route guard to be able to see if you have like a wallet or something like that already. That will let you enter in these other routes. Otherwise, it will lock you on the landing page. So you can like pop a message to people saying you should start by installing the Argentext wallet or something like that, as we have here. But it's not this one. Yeah, continue. Again, after this, we have this helper to get the contracts to work. Like if you compile your contracts with our repo, our scripts will generate like a JSON with the address already for you. So you just have to put here your contracts, and it will get the address, instantiate the contract and stuff like that. So it's very easy to use. You just need to change the network, because if you are using the testnet, you have to change it here. The reason why it's just like that is because we were trying to make it more more automatic, but because of time and issues and problems like that, we never end up doing that. So yeah, just change here, testnet, put your contracts, deploy them, and this will hopefully work. Now, this is the guard, just to make that, to see if you have an address or not, just to split apart, you know, if you are in the right route with the account. So it's not that much. You can look at that. It's just an next thing. And at last, we have the contract itself, or the component itself that interacts with the contract. It's basically, for instance, it's not here. Yeah, it is. What we do is just, forget this for now, this line. What we do is just getting the contract with this hook from React StarkNet. We pass it the ABI and the address, and then we can use these other two hooks to make calls and invokes. Like, it's the same. How do I scroll? This is not my laptop. So we pass it the contract that we get in the previous call, you know, the method, and args if it have any on the call. And this will return like a data object with all the information that comes from that call, and other cool stuff like errors, a loading to put a spin or something like that if you want, and a refresh callback as well, so we can always call this whenever you want. But this is pooling as well, so you can just left it doing its stuff. It's React, so it will automatically change anything if anything changes in this data object. For the invoke, you have this callback function as well. You can call it whatever you want. In this example, we are calling it when we click a button. Unfortunately, we will not work in DevNet. This is the part we will fail, is making the invokes. Everything else is working fine. We try to sort that out before this bootcamp. But yeah, and I think about the code, the important stuff is just that. You can start by messing with this repository if you want to use this on the hackathon. To run it, it's just at the root of the project. You can just run this command, run UI start. It will launch the application. And we can see it right here. Let me just check if everything is all right. Yeah, seems right. You need to change your Argentex wallet to localhost if you are using the DevNet. I'm doing that. Deploy a wallet contract just to be able to use our application.
You mean testnet?
No, I'm on the DevNet.
Oh,
I will.
I thought you said yesterday.
It doesn't. Yeah, as I said, it doesn't work properly because we can't make the invokes. But just to see the application is enough.
Can I ask a question?
Yeah, sure.
How does it even install? How does it even deploy the wallet if it has no funds to start?
Yeah, actually, I think they will be able to explain that better.
Sure, that's a great question. So currently, you don't pay to deploy a contract on StarkNet. Oh, sorry, there's a mic, it's easier. So Ariel is here. He was here? He's not anymore. Okay, so you don't pay to deploy a contract on StarkNet. It's free to deploy it. So deploying your account contract is free. And so you know, StarkNet is under development, so we're still a bit in between. Technically, you can send a transaction directly to any contract today. You can do that, and you don't pay any fees. In a few weeks, this will change, and in order to call a contract, you will have to call an account contract first and pay for fees. But right now, you don't pay to deploy a contract. Does it make sense?
How will you, after that, how will you deploy the wallet?
So deploying the contract you will still need to pay for that. No, I'm sorry. In the first steps, you still won't have to pay for it. And then I think we're still answering that question. We're not sure exactly how we're going to do it.
You have like a chicken and egg problem, like the wallet
Yeah.
is the contract, but you need money to deploy the contract.
Yeah, definitely.
I actually had that same question myself.
Ariel was here earlier. We can bother him with it later on if he shows up again.
Thank you. So, let me sort this out a bit. We have we're having the same issue. Yeah, so, but because this is not really working on DevNet, so that's all I have to show you guys. Now, my colleague will continue.
Is this, is this mic working or not even? Okay. Hello again. So just a quick thing. I already asked, but a few people came in. Who is here today that wasn't yesterday? Just to. Okay, there's a few people. We're gonna build on top of what I already went through yesterday. So I don't know if you already studied Cairo a bit, or if you know anything, or just coming in blank. If that's the case, then we can we can talk afterwards. This is going to be just pretty much first half of the morning to explain some things, and then to go into practice. During that second half, if you want, we can, I don't know, give you a quick course, I guess, or just answer questions if needed. So yeah, in general, how did the exercise yesterday went out for you? I know that a lot of people had technical issues, which is expected. That's partly the reason why we're here. Did anyone manage to submit a contract to write some unit tests or something like that? Okay, a few people. So yeah, today we're going to do things a little bit differently. So yeah, there's just a couple of topics that I wanted to explain, which is the account contracts that we're just talking about, and the L1 to layer 2 messaging. And because that one is actually a bit tricky to explain, or to show how to write the unit test for that, which is what I did. Instead of just explaining you and then expecting that you will do it yourselves, because there's going to be a whole bunch of other technical issues that we'll probably bump into. What I'm going to do is I'm going to show you the actual solution instead. And then during the practical parts, everyone can just keep going at their own pace. If there's still technical issues to solve, we'll go through them. The people that are already set up, they can continue writing a contract, or even thinking about what they may want to do for the hackathon, because I think that way it works best for everyone else. And if, again, if anyone has questions, or we can always discuss. And again, feel free to interrupt me during the talk if I'm going too slow, too fast. I usually do a lot of both of those things. So, so on the repo that you have access to, the public one, I already pushed last night a branch solution -day one, and in here you'll have the code that I a solution, maybe an overcomplicated solution for the problem from yesterday, the rock paper scissors game, and that's probably the first thing that that we should get started with today. Yeah, so here it is. Couple things first. So we already went through what most of these things are. So this is a struct for a game, and then there's a bunch of storage variables here. I already talked a bit about this yesterday, but one thing that this was just a technical choice. Instead of storing an actual struct for a game, I stored individual mappings for each of the values. The reason was just because when assigning just a single storage, a single of these elements at a time, so when a player moves, I want to set his address and his move. Then the second player moves, and I want to update just these other couple of fields. And then when someone wins, I want to update this one. And the way updating structs works right now, you still need, even though you're just updating that single field, you need to explicitly set all the other ones. So reading the code for that would be a little bit clunkier because you'd have to be repeating yourself a bit. So just for readability purposes, at least, what I'm doing is setting each of these fields in a separate storage variable so that I can read and update each of them independently. And I think, in my opinion, at least in this case, it's a little bit easier to read. If I were setting the entire struct or a big part of the struct in a single place, then maybe the struct would be more readable. Another thing that I did here, and not sure if anyone picked up on this yesterday, that I mentioned that there could be some kind of a security exploit in the way that I presented the problem. So player one moves, then player two moves, and then someone could claim a win. Did anyone notice what the potential problem there was? Yeah?
Well, I guess player two can see player one's move.
Yeah, exactly, because everything, yeah?
So then why does the second move have to be hashed?
In this case, it doesn't. In this case, just to keep I just went for that approach to keep the API consistent. Because otherwise it would look, I would be writing even more code that would be kind of beside the point. So both players submitted the same kind of transaction, then both players reveal that same, their value, and it just looks, even though it's not as efficient, it just looks cleaner for the purposes of this. But yeah, in theory, only the first player needs to submit a secret move, and the second player doesn't need to do that anymore. But so the idea for everyone else is that I can't just submit a transaction to StarkNet, but this would be true for Ethereum as well, saying that I want to play rock, because that would be public for everyone else to see, and player two could just go to the Explorer, to Voyager in this case, and just see, yeah, he played rock, so I'm going to play paper, and I win, easy. So the way this works is it's called a commit reveal scheme, where instead of submitting literally the move rock, so let's say I'm using just felts here, but I could just decide to submit the string rock. It would just be a little bit harder to then compute the calculations because they're strings. So instead I submit a hash, which is I compute off-chain. Maybe the UI does that for me. And that hash will be, for example, concatenating rock along with a secret password that only I know. And that hash is what's stored on the only thing that the contract knows for now. And then after player two moves, then I need to reveal that move, which is telling the contract what the move was and what my password was as two separate arguments. And then the contract can do the same process, concatenate them, calculate the hash, and the hash should match the original one. So it's just a way for me to commit to a move in the blockchain without yet telling the blockchain what that move was. There's a few problems here. This isn't really production safe because I can just submit a random hash even though I may not even know of a valid move that would translate to that hash. So in this case, if I submit a random string, I would just be locked out. There's no way that I could reveal. But that again, that kind of thing was already a bit too much, I believe. So I just went with this for this workshop. So with that out of the way.
Just one question.
Yeah.
So basically that means if he submits rock and he writes, I don't know, I want to submit rock, then he's already safe because no one knows what is.
I'm sorry.
Like when he submits a rock, then you see the hash value, and you can find out that he submits rock if that's what I understood correctly.
No, so what you submit is not the hash of the string rock. It's you take rock, you concatenate that with some random password, and that hash is what you send. So at that point, only you know the password, supposedly, and then you need to reveal the two individual values, and the contract will do the same process of calculating the hash, which should match the original one that you sent.
Okay.
Yes.
Can you explain, I don't understand the game ID parameter. So on your storage,
Mm-hmm.
like you said, setting storage is basically like the syntax of a function.
Mm-hmm.
You've got a different parameter and different return. Like what is that doing?
Different parameter and
Like-
different return.
Player one storage
Mhm.
takes game ID parameter, and the return value is player one.
Yes. Okay, so
Yeah.
okay, so I'm not sure exactly what where your confusion is, but so essentially by adding the game ID as a parameter to every storage value, this is a mapping or a dictionary. So if I call player one storage with one, then I'm asking what's the player one for the game one. So that's just what it is. So for game one, instead of having a struct with each of the different members somewhere, I just call each of these storage variables with that game ID.
So you have multiple games. Okay,
Yeah,
So
so-
it's starting a map. So each one of those storage variables is a mapping.
Yeah, so the way this particular one works, and this would be, there would be many ways to do this, but in this case, you call the play function, and you submit a game ID and your hashed move, which is that string already with the password encoded and so on. This game ID can be anything you decide, as long as that game is not yet played.
So if you left off the game ID parameter when you declare the storage variable, then it's just a
You would be,
slot?
that contract would only support a single game, a single instance of the game. So yeah, going back to what I was saying, because I went for this approach where instead of starting a struct, starting multiple storage variables, I also ended up writing a game function, a view function that just does the opposite, takes all those storage variables and returns the struct. So that's in the test I could just read this as if it were a struct, just for, again, for readability, and maybe for the UI it's also a lot more comfortable to do it because you're just doing a single call to the contract instead of multiple ones. So this was just for I guess for UX reasons, if you can call it that. So going to the play function, this has maybe a couple of new things to explain. So the approach here is I'm reading the current player one and player two for this particular game ID, because this may be the player one submitting a move and then it should be empty, or it could be a game ID that already has one move and then I need to submit to register player two, or it could be a game that is already fully played and then this should just revert. So in this case, well, first of all, I'm getting the caller address. This, I didn't actually explain this one yesterday, but get caller address is a function that you can import from standard library. And it tells you what the address is from the account contract that called this function. And like Henry was saying earlier, currently you can call this function directly from your wallet without going through an account contract. and that means that in that case, get caller address will be 0. And in this case, we need to prevent that from happening. And there's a bunch of conditions here, or I mean, I don't think we're preventing that from happening. I'm not sure if I even did that. Yeah, if player one is 0, this still works. Yeah. So right now you can play this as without going through an account contact, but that would be something that you may need to consider at least while those things are not yet enforced. So we need to ensure that the game is not finished, and just an easy way to do that is to just check that we don't yet have a player 2. And again, like I said yesterday, if player 2 is already set, then this assertion would fail. But in this case, by default, the storage variables are 0, so without a player 2, this will work. We also need to assert a few extra things. So assert that the hash is not 0. This is a very weak check, but just some sanity check for here, because he can't submit a hashed move that is 0, but he can still submit some other random stuff that doesn't actually, that's not a valid move, at least right now. And assert that if the player 1 has already played, then player 2 cannot submit exactly the same hash, because he could try to do that because that hash is public, and this would always be a tie. So he can play the same move, but he needs to choose a different password. And then by the end, once all these checks are done, we just check if player 1 is 0, that means we're setting player 1. So we write both the player 1 address and the hashed move that is submitted. Otherwise, we do the same thing for player 2. So both players need to go through this. And then afterwards, both players also need to go through the reveal phase, in which they send the same game ID, the move, and the password, or I called it salt here. And it's going to do that process that we explained before. One detail here is that it doesn't actually have to be player 1 and player 2 that calls this. So because this password here is the secret element, if I know the password that Jill submitted, I can reveal the move for him. So we already have that security encoded there. We don't need to check or to restrict it to just be called by the player himself. He can delegate that to someone else if he wants. So we read both players, we read both hashed moves. Player 2 cannot be 0, which means that this can only be called once both moves are committed. The move needs to be in the range of 1 to 4. 4 is non-inclusive, so this is 1, 2, 3. So I just went with an approach where 1 is rock, 2 is paper, 3 is scissor. And that just simplifies a bit the math down there to check who won. Then we compute the hash for move 1. Oh yeah, so because we don't, because the caller is not necessarily the player, what I'm doing here is computing the hash for as if, so if this was player 1, what would be the resulting hash? And if this was player 2, what would be the resulting hash? The reason for that is that I'm hashing it based on the move, the password, and the address of the player. So that just one extra layer to make sure that if both players try to play the same move with the same password, that will result in a different hash. So it's easier to prevent collisions if people try random things like a password of 1, 2, 3 and stuff like that. And that, so by the way, this hash function, I should go through that first. So this hash function receives the move, the password, and the player, and it's just a regular function that is down here. This is not an external or a view function. And it's just, this one calls the Peterson hash, which is one of those built-ins that I was explaining yesterday. And in this case, we do need to use the explicit syntax for the implicit arguments. So the built-in that we have is the Peterson pointer. But this hash2 function, which is what calculates a hash, it receives a built-in called hash pointer that in this case we want to use the Peterson one, because this could support different kinds of hashes. In this case, this is the one we want to use. So we call hash2, but we explicitly set with a name argument that the hash pointer, which is the one that hash2 expects, is going to be the Peterson pointer. And the rest of the stuff about implicit arguments is gonna still work. So this Peterson pointer will be updated and chained together, and will be also returned implicitly, the updated one right here. So we're hashing the move and the salt. Then we're taking the result of that and hashing it once again with the player address, and that's the final result that we have. And in the code, or after computing those hashes, if the hash that we computed for with the player one address matches the move that player one submitted, then that means we're revealing the player one. So we write the unencrypted, let's call it that, move to move one. Otherwise, if it matches the player two, we write it on move two. Otherwise, that means this doesn't match and we don't actually write anything. We're not failing here. The transaction will still execute. It just won't do anything. We could revert here with some kind of error message. I just opted not to.
Sorry, question. Couldn't reveal be called when the second move is in?
I'm sorry, I didn't understand.
So first you send a hash, then you reveal right afterwards, but
Mm-hmm.
you have to call that again, right?
Yeah, so that's what I think it was you asked as well, that player two wouldn't actually need to submit an encrypted move and then encrypt it. He could just directly call something else to say the move explicitly. I just went for this approach just to keep the API consistent. It looks the same for both players, which means that the code is also simpler to read. It doesn't, otherwise you have player one calling one function, player two calling a slightly different function, and then player one calling a third function again. So it would just be...
I mean, with this setup, couldn't you just run reveal after the second move is in? Save the transaction. You just call reveal after you have move two automatically.
Oh, you mean, I mean, not explicit like this, but...
Yeah, basically like if there are two moves, just run reveal again.
yeah, so here.
Is that possible?
So here it's not possible because you don't know the actual move and password here.
Right.
You could, like I was saying, in this particular way, it's not possible. By the way, one detail here is that you can notice that inside of each of these if-else branches, I'm explicitly returning. I shouldn't need this. So, it would just be a lot more cleaner to just return at the end because it's just the same thing, and then this else branch wouldn't be needed. So this was the actual code. The reason for that is that, and I probably can compile this or try to compile this right now and show you, is that this goes into the revoked references issue that I was explaining yesterday. See if it shows what there could also have been some update that changes the error message between the first time I wrote this and today. Yeah, okay. So you can see here that it's complaining line 108, which is, yeah, it's the beginning of the reveal function. It's trying to retrieve the implicit argument syscall pointer. Reference syscall pointer was revoked. So essentially, the way I think about this is, like I was saying yesterday, that these implicit arguments that need to be passed around, because there's some branching here and some more complicated logic, the compiler isn't yet able to keep track of all these pointers because they're being potentially updated when calling hash functions, and in this case when writing to storage and so on. the original way that I had to solve this, and it's something that you may run into, is to do something like this, where you declare a temp variable and you assign it to, you create a temp variable with the same name and you assign it to the current one, and is essentially rebinding that variable to something new. And that means that you now have a new syscall pointer here that the compiler is able to track. I can't explain you the technical reasons about why behind the scenes this is still needed. It's just the way I reason about it.
I can explain.
Okay, good. Then you explain while I copy and paste this to, to a couple of places.
So, no, I think it's okay. So basically, the way Cairo works is that it's fixed memory. You never go back to where you were before. And it works with a pointer, right? With a stack pointer. So before you enter the if, all of these variables that were defined before, so these are built in, you know, it knows where it is because it knows where it is related to where it is before, right? When you call a function, it jumps to a new location in memory, and then when it finishes calling this function, it comes back, but then it lost all its references, right? So you need to store before the memory cells you want to use after calling this function, so that you're able to access them later on. When you're entering an if and else, basically here you're branching your code into two different directions, and it could be that you execute over 100 cells here and over 10 cells here. If your code runs on different lengths of codes, then the references you had before are lost. So that's why you have to declare them in both branches so that you're able to find them later on. Does that make sense? It's weird, right? But that's how it's works. This is something that...
Sorry to interrupt you. I'm very, very sorry. I just wanted, if anybody's drinking inside, it's just because it's a very strict rule that they have here, that you're not even water. I'm sorry, my friend. Sorry to interrupt, Andy. But yeah, it's a rule. So we're guests here. If you guys are okay with that, I would appreciate it. Thank you so much.
So this is part of the, things that make Cairo a bit harder to use in Solidity. This is something we're considering making more simple. It will only get more simple, less complex from here. So this is how it works for now. So when you have if and else, basically if you have an if, you should declare an else. And if you want to reuse variables later on, you should declare them in both of your branches. Okay?
Cool. So you just copy paste that at the end of every if and else you could have.
Yeah, more or less.
Yeah, so in this case, then an unfortunate part about that is that I explicitly need to create this else branch, even though I didn't really need it. So because in this case, at the end of all this branching, I'm actually just returning. That means just to make this more readable, instead of doing all this, I can just go and do what I had previously, which is just like so. But again, I need to explicitly return in every branch. It's just a technical detail that right now we need to live with, but it's probably the one thing, and I struggle with this myself, that once you get, if you find that error by yourselves and you have this explanation in your mind, you're gonna spend maybe some time on Discord trying to figure it out. I was lucky enough to be working with someone that already knew Cairo more than me, so I was able to get a quicker answer. He was actually the one that explained to me that in this case I can just return directly and it's easier. But yeah, it's one of those things that's it's not so intuitive to understand at first. Now you know. So yes.
So if we have to return all the existing variables from this before we went into the move with the branching condition, you would think that you could just add some kind of syntactic sugar or something like that to return that. Does that mean like there are other cases where you don't have to return everything? So like it sounds like it's either you're returning all the existing variables or
I'm not sure I understood the question. So you mean if there's a case where I don't need to reassign all these 3 and I may just need 2 of them?
Yeah. Would there be cases like that?
Not 100% sure. So I would imagine that yes, if the rest of your code only depends on 1 or 2 of these, then probably that would be the case. But in StarkNet, you pretty much always need these 3. So maybe that can be a thing in Cairo, but in StarkNet contracts, I would guess not so much.
I think when I was writing just a getter function for one of the storage bars, you don't need them. Is it possible?
I'm sorry?
I was just writing a getter function for one of the storage variables, and I didn't need to put them, and I think it was compiling fine.
For storage functions, you need at least this one.
No, like the 3 of them.
Oh, you mean a contract that just reads from storage?
But a function that was just reading from the storage.
Oh, yeah. Yeah, maybe that's the case, yeah. No. But yeah, in that case, then you probably just need to keep the reference for that one and not the other ones that are unused. All right. And so just to finish this example really quickly, lastly, just a finish function, which, again, for simplicity's sake, finishing the game could be done on reveal. So if the second player reveals and I already have the first one, then I could just deal with that logic right away. In this case, just to keep things isolated and to be able to test things individually and explain things individually, I just separated that to a separate function. So in this case, the winner needs to do a third call. I mean, in StarkNet, that's not much of a problem. We come from Ethereum and we're used to trying to optimize to not pay gas. In here, that wouldn't be such a big deal, especially while gas is still free. We don't need to pay fees for now. But yeah, computing the winner is just grabbing, once again, both of the players, both of the moves, and calling this other function where the more, I guess, complicated part to compute is, where we need to actually take those 2 numeric values, so 1, 2, 3 for each side, which we already have, and decide who won. And this is just by kind of luck or math being fun. I typed out all the combinations here just to make it a bit easier to understand, because these may look just random. But generally, this is the pattern. Because those are sequential numbers, this is the pattern that tells me who won in each kind of combination. So if player 1 is 1 and is a given number, and player 2 is the next number in the sequence, then in all cases, player 2 is the winner there, and so on and so on. If both moves are the same, it's a tie. And obviously, we need to assert that both of those moves are not 0, and this is what prevents a player from calling this function while one of those moves isn't revealed yet. And then, so with this logic in mind, in the comments, it's just a matter of checking for each of the 4 or 5 branches and returning whoever won in that case. And then on the rest of this finish function, you could do, like I was saying before, you could, after computing the finish, you could mint an NFT for the winner, or you could include here a prize pool where when you play, each player needs to make a small payment and then the winner gets the full pot or something like that. You could think about all kinds of use cases here. Any questions? Okay, so for the second thing today, I should probably just show the tests, just so that you don't have to take my word for it and actually see that this works. I think this is the command. So while they're running here on site, I think I have DevNet running. Yes. So while tests are running, let's just go through them really quickly. I I mean, the most relevant ones are, well, there's some checks here to check that it fails if player 2 tries to use the same move as player 1, the same encrypted move as player 1. It fails if the same player tries to make both moves. Then some similar logic for reveal, and then the main test is just computing that for every combination of rock, paper, scissors, it computes the winner correctly. So this is just calling directly the compute winner function, which is one detail that I forgot to explain. So this compute winner, it's called within the finish internally, but it's also declared as a view function just so that I could, in this case, just so that I could call it directly in the test and create a unit test to just test that part in isolation without having to make a bunch of transactions. So now for the accounts abstraction part. So as you saw yesterday already, we're using this OpenZeppelin package. This is just pretty much a port from the Solidity OpenZeppelin repo to Cairo. And this is where the account contract that we're using for the moment, in these tests, that's where it comes from. So there's, as far as I know, two main account contracts for now. There's the one from OpenZeppelin and the one from Argent, which is the one that the wallet, the browser wallet is using. But they do pretty much the same thing. And the source code for the OpenZeppelin one is right here. So in this case, actually in the unit tests, so before running the unit tests, I'm deploying two account contracts, one to represent player 1 and another to represent player 2. And then instead of interacting directly with the rock, paper, scissors contracts, I'm interacting with the player contracts and asking it to invoke a function targeting the rock, paper, scissors contracts and then calling play with these arguments. So that in a regular invoke, you would see something like this, where you're invoking a contract with a function and some arguments. In an account contract, you have an extra argument, which is which contract am I then forwarding the actual call to. And the way that's done is actually pretty simple. An account contract is a contract, pretty much, that just handles the logic. So it knows what your public key is, because it needs to map to check that the signature that you sent is actually signed by you. There's a nonce to implement the same logic as a nonce in Ethereum. Then there's some setter functions, a constructor, a function that validates a given signature, and then this underscore execute function is the main entry point. And when you submit it, when you call a transaction through your account, this is what you're going to do. And it's kind of a metaprogramming kind of thing, where similar to where in Solidity you can call another contract with a piece of byte code, the encoded call data. You can delegate that to another contract, or do a delegate call directly. It's kind of the same thing that's happening here. So when you do that, this asking player 1 to invoke a given contract, behind the scenes, in this case the StarkNet JS library is encoding that into the call data that needs to go to the rock, paper, scissors game, but is then calling our execute function with that, which is gonna check the signature, and if it matches, it does the actual call with this account execute, which is again in the library side of things. Accounts execute. And this is doing some more complicated logic because it actually supports multiple calls, so you can encode multiple individual calls to smart contracts in this call data. So it's doing some recursion on this list to send them all forward. But that's what happens kind of behind the scenes when you do a transaction. You're going through some logic like this. This particular account contract is fairly simple. It does this. it does what you would expect from a regular account in Ethereum. It has a nonce, it has a public key, and it verifies your signature. That's the basic stuff. But you could then think about other use cases for this account contract. So a multi-sig contract could be implemented as an account contract where instead of a signature, you need to receive multiple ones, and multiple people will need to sign off on that. Or an account contract that allows you to, instead of holding Ethereum to pay for fees, you could just hold stablecoin and swap that on the fly on every single transaction. So you'd be able to pay fees with any given token, kind of, or indirectly. And maybe even for accounting or what's the word? Auditability, where you need to somehow keep track or emit events for things that happened through your contract for some off-chain tooling or for auditing, which is useful in some cases. So yeah, you can probably go crazy with that and implement weird account contracts for the hackathon, maybe. Any questions about that? Yes?
Kind of, maybe. How does it even, how do you even, without some, okay, I guess I'm confused about like how you even call anything on the account contract without having some funds. Like, does that contract have funds already? Like, in Ethereum, to call a contract, you have to have some ether, right? So,
Mm-hmm.
if this is already a contract, where is it running when you execute code from it? And how do you do that without having some gas?
Oh, yeah.
Sure. So, there's no such thing as an externally owned account in StarkNet.
Yeah.
We're standing on the shoulders of giants, and what we did with StarkNet is something called account abstraction, which is something that was long sought after on Ethereum, which is basically decoupling your account and the way you sign for stuff. So things are different than Ethereum because on Ethereum, you link the person doing the transaction object, and the person who is actually doing the payload, executing the payload, right? So your account, the one who is signing for transaction, is also the one who is doing actions on the chain. Here we decouple that. So that's why every account is a smart contract wallet. Now that's a good question. Like, how do you enforce fees? How do you pay for fees when calling a contract? And this is very much something that we are in the process of rolling out. So the way it works currently is that fees on StarkNet are not mandatory. You can send transactions without paying fees. We are rolling them in. So right now you can pay for fees, but you don't have to. Within the next few weeks, you will have to pay for fees. The way we do that is basically that right now you can send your contract to any kind of contract. You can send a transaction, a payload, to any kind of contract, and it will be executed because there is no fees. Soon, the only kind of contracts that you will be able to send transactions to will be account contracts. So contracts that have a specific entry point, which is called execute. Now, in execute, there will be a function where you pay for fees. So basically, you will call your contract and say, I'm willing to pay that much fees, and it will be paid at the contract level, at your account level, at the account level when you're calling the entry point. Does that make sense?
Yeah.
Anyway, it's a deep topic, and we can talk a bit more about it if you're curious, but specifically, one of the issues we have with that is that on Ethereum, since you're paying with the transaction object, if you're sending a transaction that won't pass, then it's possible for the person who includes your transaction to take the fees, right? It's what prevents spam. It's what prevents you from sending a shitload of transactions that won't pass at zero cost to you, that will cost something to the sequencer, to the person processing the transaction. Unfortunately, since on StarkNet, you send code that you prove executed correctly, if you send code that can't execute correctly, you can't prove this. You can prove that a program executed correctly. You can't prove that the program did it. So we're a bit looking at how we can implement that.
first validate that the transaction is executable, and there are some fees associated to it, so that the sequencer knows that he can look into the second part of the transaction and will pay for that a minimum fee. And the second part that will be executable. Another design we're looking at is having two fees associated to a transaction, one which we call the red fee and the other one which will be called green fee. The red fee is something that the sequencer can take no matter what, and the green fee is something you can take if the transaction executes correctly. Now, if the transaction doesn't execute correctly, then you can still get the red fee. But anyway, if you're interested, I can just talk about it more.
So the funds always stand in an account, which is a contractor.
Yeah.
So how do you like deploy that contract in the first place?
Yeah, so right now you don't pay for contract deployments. Eventually, probably you will deploy a contract from another contract. We also have this weird concept that's what it's not that weird actually when you think about it. You know, who here has deployed an ERC-20 already? Okay, who took the boilerplate open Zeppelin contract and just deployed it? Right, most people. So what happens on Ethereum is that you have the same contract that is deployed over and over and over again because everybody uses the same thing. So what we're doing right now is we're decoupling contract code and contract instances. So eventually, when you will deploy a contract on StarkNet, you will deploy the code, so you will deploy the contract, which will be a class, and you will deploy an instance of this class, which will be an instance of the contract. So you will have fees associated to both, because they're both different and both have different things. The fun thing about that is that you can deploy a class without deploying an instance, and if you start doing things like delegate call, you can delegate call, you don't delegate call to an instance, you delegate call to a class. So you could have a contract that delegates his calls to a class that was never deployed before. Anyway, fun move. Are there other questions?
All right. So in the meantime, I was told that coffee break is in 30 minutes, more or less. So what we're going to do until then, I will start, not necessarily finish, showing or explaining how layer 1 messaging works. And then after that, either we continue if it takes longer than expected, or we move directly to getting hands-on. So like I was saying on the slides yesterday, the idea for today is that we'll take this implementation that we already, in this case that's the solution that we already have. There is, maybe you've looked through this, there is already an NFT contract, some boilerplate here that has some to-dos in the middle. That's mostly because what I wanted to do is simulate the ability to bridge an NFT. So let's say you would mint an NFT for every winner of the rock, paper, scissors game. You could then be able to bridge that NFT to Ethereum, maybe to publish it on OpenSea while the NFT community doesn't move to StarkNet or something. And also on Ethereum sides, you have the ability to bridge it back to L2. So that requires a few different things, both in the code and in the infrastructure. The first thing is that because we're communicating with Ethereum, we need Ethereum. So, and because we're developing locally, instead of actually communicating with Ethereum and again waiting for transaction confirmation and needing gas and so on, for local development, I just included also a Ganache server here. So this is going to act as our Ethereum. And the way or not, I shouldn't say the way L2 messaging works, because I'm not going to go that deep into it, but from your perspective as a developer, what happens is that so periodically StarkNet is going to sync with Ethereum. It's going to send all the proofs and the state changes to the verifier, like we were saying yesterday. and along with that, it's also going to include whatever messages contracts on StarkNet sent to L1. So within your Cairo StarkNet code, you can decide to send a message to L1, and whenever the next checkpoint is between StarkNet and Ethereum it happens, that message is going to be included there, and it's going to sit then in a contract in Ethereum. So one way you can think about this is, I don't remember when I saw this analogy, but if you think as Ethereum and StarkNet as two different planets, trying to go from Earth to Mars, if Mars is on the other side of the sun, your message will take a lot longer to reach there. But if you happen to send a message while both planets are in the same position in orbit, then your message will be a lot faster. So it can be a bit unpredictable to know when you send a message from one side to the other, when it will reach it, unless you're actually trying to time it correctly, like NASA would do to send a rocket to Mars. But yeah, just to explain that there can be some unpredictability in how long those things take, but it's in the scale of hours.
That's about batching transactions together?
Sorry?
Is that because of batching the transactions together on L2?
It's because StarkNet, well, you can call it batching, yes. So StarkNet does some periodic checkpoints, which is so you're sending transactions to StarkNet, and within StarkNet they get accepted. They go to the sequencer and the prover very quickly, but then they only get confirmed on L1, which is the next step in some periodic checkpoints. So you can keep going in StarkNet. You can build on top of those transactions, and every once in a while they'll be checkpointed to Ethereum. So if you see, I think I was with you, you submitted a transaction yesterday, and you get a notification saying that the status is accepted on L2. So that means that your transaction was, well, accepted on L2. And eventually, if you wait a little bit longer, well, not here locally because we only had the DevNet, but after a while it would change state to accepted on L1.
But is that the same, is having those transaction confirm on L1 the same bridge as if you want to send a message to L1?
It happens in that same checkpoint, yes.
Oh, really?
So basically, when you send a message to L1, so the way it works is that StarkNet executes a bunch of transactions off-chain, right, and batches them into blocks. And periodically, these blocks are coalesced into a proof that is then sent to Ethereum to say, hey, we moved from block A to block F. And this is what happened in between. So we update the state to Ethereum. We send the state, the difference in state between block A and F. And there is also a number of messages that are sent. And this is when your payload are distributed. So when you're sending a message to Ethereum, when the proof is sent, all the messages are sent. The frequency of proof is not fixed. It depends on the usage of the network. Right now, it's every 2 hours on testnet and every 12 hours on mainnet, which is quite long. When you're going from StarkNet to Ethereum, it takes the amount of time between two proofs. When you're going from Ethereum to StarkNet, it takes less time because StarkNet basically is able to read from Ethereum, and so it takes about 10 blocks to go from StarkNet from Ethereum to StarkNet.
What I was just thinking is you could have like a separate bridge just for messaging, right? You could like talk to
I mean, we could, but the thing is, here, what's powerful with this bridge is that you don't have to rely or believe a validator. It's mathematics, basically saying, hey, look, mathematically speaking, this happened on StarkNet, and this message was sent. You don't need to trust us that this happened. And this is what makes it powerful. This is what makes it something that relies on math and not game theory. You're not hoping that the validators will behave honestly. You're trusting math that this happened in StarkNet. Does that make sense?
Yeah, but like most people would just end up using other bridges, right? If they want.
Yeah, but well, on that, if you look at bridges, they're probably the least secure and the most exploitable part of the ecosystem nowadays. And yeah, in here, you're not relying on external validators, and sometimes even, well, in some bridges, it's even shadier logic. Here, you're just relying on the security from Ethereum itself. So you're not making any kind of security trade-off there in order to have that bridging.
Technically, the Ronin exploit that happened a few weeks ago happened because the validators got compromised. You can't have that here. I mean, if the validators, I mean, there are other attacks, but if the validators get compromised, they can't send messages saying, hey, this happened. So of course, you will have applications on top that will say, oh yes, we want to drive this lower than 2 hours and everything. Just like what is happening on optimistic rollers, right? I mean, withdrawals take up to 7 days, and then you will have an ecosystem of apps that will provide you liquidity faster. The thing is, with StarkNet, the more there will be transaction, the higher the frequency of the proofs, and so the lower the time capital will be immobilized, so you can hope that this will be cheaper. And probably for some applications, some people will want to go faster. For some others, people will have to wait. You know, you can have liquidity providers for ERC20s. You can't really have them for NFTs. So, and also I want to mention that the bridge we have, I mean, when we think about bridging in the blockchain space, you think about assets, right? You bridge tokens or you bridge NFTs. But this is a very narrow view of the world. You could bridge way more. You could bridge permission, you could bridge voting, you could bridge instructions, you can bridge basically anything. The basic building block we give here is not a way to transfer assets, it's a way to send messages. So you can build your own bridge, you can build your own cross-layer application. I mean, the bridge just passes data through, and then you design the cross-chain, the cross-layer protocol you want to design.
I'll ask you more questions. I have more questions, but I'll ask you.
Sure, happy to.
All right. So in the meantime, I moved to a different repo, which is the private one where I had already the solutions implemented, which is what I was going through now. So if we go back to that, so on the NFT on the Cairo side, and this is just a standard ERC 721. I'm not going to go through this. It's pretty much copy and paste and importing from OpenZeppelin. The important part here is that, like I said, I wanted this contract to be bridgeable between L1 and L2. There's going to be a Solidity contract on the L1 side. And in this case, so I need this contract to know what the address of the L1 contract is, because I'm essentially going to be sending a message saying I want to send a message to the L1 contract saying that this particular NFT has been bridged and the address of the new owner on that side is this one. So I need to include a storage variable here to know, I mean, it could be a hard-coded value if that was the case. In this case, I wanted to make it configurable. So include that. In this case, minting happens on StarkNet side. So what I'm going for is that the contract is minted here. It can be bridged to L1, and the way that will work is that once I bridge it, the owner of that token on StarkNet will be the contract itself. So I'm essentially locking my token away in the StarkNet contract, and a corresponding token should be minted for me on L1 side. And when I bridge it back, I want to burn the Ethereum side and release it back to me on this side. You could also have the other way around. You could burn it here and always have the supply locked in the contract on L1. Again, the messaging is just to exchange data between both sides, so you can go for whatever approach you want. One thing you can't really do is that because addresses are not compatible, you can just say something like, I want to transfer this token to the same account on Ethereum, because that same account doesn't exist. You need to explicitly say what your address is going to be. And so I have an external function here to bridge to L1, where I say my L1 user is this. And this would be your Ethereum address converted to a felt, because those are both numbers. And fortunately, an Ethereum address fits within a felt. So that works fine here. And my token ID. And my token ID here, just for simplicity's sake, this was supposed to be a uint 256, and that's how OpenZeppelin implements this ERC721. They're all the token IDs are uint 256, but because the way I'm minting this is just sequentially, the first one is going to be ID 0, then ID 1, and so on. It's not realistic that I would mint all those tokens. And then that would mean that I would have to deal with the fact that 256 uints are 2 felts here. I would have to send 2 felts separately in the data to L1, which means that there I would have to decode those 2 ints and merge them into the actual ID. So it would just, again, be a slightly more complicated logic. So for simplicity's sake, I just simplify things to say that it's a single felt, so I'm just gonna convert back and forth because I know for a fact that only the low part of this uint 56 is used, so I'm just gonna use that. So to bridge it, yeah, I need to convert. I need to grab the token ID that I'm trying to bridge, convert it back to uint 56, to then ask ERC721 who the owner is. And I do that because I need, I'm going to do transfer from the owner to myself. So self here is the get contract address, so the contract itself. So I'm asking the token library to transfer from its original owner to me. And this internally, if we were to look at this function, this only works either if the caller is the owner or if it's approved to transfer with the approval mechanics. So I need implicitly, I need to be approved to spend this token, let's say. Then we allocate some data. This is a generic alloc function that I don't think I showed you yesterday, but yesterday I created a tuple of 3 vectors and then I casted that to, I used it as if it were an array. I could also do something like this where I just allocate some piece of data. In this case, I'm declaring it as a pointer to a felt because that's what I need to send over the bridge. And I designed this message as just needing a payload of 2 elements, which is, again, the destination address on the other side and the token ID. So that's the only thing I need to assign. And of course, I need to read the contract to which I'm sending the message. And then finally, the main thing is just this send message to L1, which again is a function that you can import from the standard library. And you just say, I want to send a message to this account, and this is the contracts on the other side that should receive that message. My payload size is 2, and my payload is here. And we're going to see in a minute how to handle that message on the other side. There's actually one difference there in how you handle messages on L1 and L2. So when you send this message, it's going to go through this process that Henri was explaining. It's going to, at some point, it's going to reach L1, but it's not. There's nothing on the other side that's going to execute that message automatically. One reason, one of many reasons for that is that if you were somehow to expect that message to trigger some execution on the other side, you could imagine that it could easily blow up, that you're trying to interact with very complex contracts and gas on the other side is expensive. Someone needs to pay for that, and it could easily get out of hand. So this message goes into a contract, a specific contract that was deployed by StarkNet on L1. That contract keeps the backlog of all the messages that have been sent in the meantime, and if those messages were consumed or not. And then you need to call it, you need to somehow trigger a transaction on L1 that's going to consume that message from that contract. And in order to consume it, it needs to be consumed from the address that we specified. So essentially, after bridging it from this side, we need to call a function on the token side, on the other side on the contract on the other side to consume the message that we're expecting and to execute whatever logic we need in that case. So in this case, we want to mint this same token ID for that user on the other side, which is that part I had already written for you. I think it was already in the sample repo, if you maybe saw this. So this is your standard ERC 721. There's a couple of details here that I'm going to go through in a bit. But essentially, I included a function called bridge from L2, which is what I'm going to call when I'm going to say, after the message has already been sent, I'm going to call this and say, hey, I'm confirming here and trying to finalize that someone transferred this token ID to this address. And on this side, we're going to essentially reconstruct the same payload that we did on the other side. And we're going to ask the StarkNet contract to consume a message from L2 that should have come from this contract and should have had this payload. The reason for this is that internally, it's essentially computing a hash of this entire payload. It's not actually storing all the data on the contract that was sent. It's just storing a hash of that for verification. And here, so kind of like what we did for the rock, paper, scissors and checking the hash, I'm asking the contract, hey, you should have a message there that should match this origin address and this payload. The contract will do that. Assume this works. Assuming this executes, that means it worked. Otherwise, this would revert. There would be no message to consume. And so after that, I just do with that what I need to do. I would mint a token to this address and with this token ID. So whoever calls this on the Ethereum side, it can be the user itself, or you could imagine the UI of a bridge system can handle this for you. You would still probably have to pay the gas fees on this side. But this part, this parameters part can be, of course, abstracted by whatever protocol you're using.
The consume message, is that just like a require or an assert statement? Like it just fails if it's not there? Does it actually run code?
Yeah, that's pretty much what it does. It checks that this message exists in the queue. It hasn't been consumed yet.
And then it throws an error if it's not there, or if it's not the right payload.
It throws a mess. It reverts if if it doesn't exist. Nothing matches this. If you're not the one that's supposed to consume it.
So let's say like the user could, for example, send like three different messages. I could have like an if statement or like a try catch, three try catch. If it's the first message, do this. If it's the second message, do that. If it's the third message, do something.
A try catch to try to consume different types of messages. Yes, you can do that. I'm not sure if it would be the most efficient way to do that. But, yeah, probably there are use cases where that makes sense. Most likely on the off-chain, you would just be waiting and polling waiting to see when the message actually reaches it. But yeah. And okay, so before going on the other direction, just let me just talk about this headers part right here. So on the constructor of this NFT, I'm sending in this case the contract address for this StarkNet messaging contract. This is the one that's on mainnet. This is already deployed, so it could just be a constant value here. In this case, on DevNet, what actually happens is that DevNet has some tooling that's where you can ask it to deploy the L1 messaging contracts to a local node, and it will deploy a contract on the fly. So I needed this to be a configurable address, and I also need a second initialize function because again, this is kind of a chicken and egg problem. On the L2 contracts, I had the L1 address as a constructor argument, but I can't do that for both sides because one contract needs to be deployed before the other. So in this case, I'm actually deploying the L1 contract first, taking that address and deploying the L2 contracts, and then going back to the L1 contract and telling him what the L2 address should be. So most of the times you may need some kind of setup like that, either in this direction or the reverse. So sending messages from the other direction. So if I wanted now to bridge my token back to L2, on this side it's a very similar process. On the StarkNet side it's a little bit different. So in this case I may want to bridge a token to a given L2 address, StarkNet address, and token ID. I need to check that I'm approved that I'm the owner or that I'm approved to spend this token. And then I'm going to construct a very similar payload, and I'm going to call the same contracts with, again, a very similar API, just with one addition, which is this StarkNet selector bridge to L2, which is, if you've ever used API encode and stuff like that on Solidity, this is very similar. So every function in Solidity has an API, a hash, which you can use to identify it, which is what gets encoded in call data. In StarkNet, a very similar thing happens, just slightly different logic. So instead of being the function header with the typed arguments and doing the kekak hash of that, I'm not sure if you can see it properly because it's a comment color, but this is the Python snippet that I used to generate the selector for that. But essentially it's the name of the function that I want to execute on the other side. And then this get selected from name, which is a function that I can import in Python from StarkNet. So if I call that with this bridge to L2, which is the name that I want to have on the other side, it gives me this uint, which is a selector that I need to send. So I need to include that. And then, of course, I burn the token on this side according to the logic that I'm using. And then, again, going back to, and this time, because this is going from L1 to L2, it's much faster to reach the other side. So if we go back to our NFT in the Cairo side, we have this new new keyword right here, which is an L1 handler. So this is not an external function, not a view function. It's not something that you can call by yourself. This is meant to be called only to execute messages that came from L1. And this one, contrary to the Ethereum side, this one is actually executed automatically for you. So when you send a message from L1 side, this one is, when that message reaches L2, this one is going to run for you. Right now, probably I can imagine some of you are going to ask, right now you're not paying any gas fees for this. I mean, gas fees are still optional anyway, but they're being subsidized by Starkware, essentially. I think it's still in the works how this is going to tie into the fee system. But yeah, so essentially this part is free for you. And it's, again, it's probably what you would expect. This function, it already decodes that payload for you. It includes an extra argument. The first argument is which contract on L1 sends this message, and then the decoded payload, which is the user and the token ID. And then we do a very similar thing on this side. So we get our current contract address, which is the one that, if our logic is correct, our contract should currently own the token that we're trying to bridge, because unless there's a bug, there's no way in this code that this L1 handler could be called correctly with it. I mean, we can send a message on the other side, but our contract doesn't include anything like that. So there should be no way for our L1 contract to send us a message trying to bridge a token that shouldn't be bridgeable. Again, that could be an exploit there if we're not careful, but assuming not, that's the case. So we should own that token, and the contract itself now, after doing some checks, and again transferring, converting this token ID to Win256, we transfer the token from our address back to the L2 user that we asked for, and that's it. So you now know how to send L1 to L2 messages. What I also wanted to show you was how to test this, because this is actually a bit of a cumbersome setup. So let me just close all this stuff. Are there questions in the meantime?
So when you deploy that NFT Cairo contract with the L1 handler, it's being automatically registered as a function that should be called whenever there's an L1 message that arrives, right?
Whenever an L1 message targeting this contract and with this selector, that ID that we showed, is sent, yes.
Okay. And what if I send a message to this selector by
Sorry?
what if I send a message to this function, like using the selector or whatever? It's just going to I can't do that. Only the sequencer can call this function? That's what you were saying?
Yeah, I actually asked that on Discord to check if it was possible. It's only the StarkNet system can call it, yes. One detail that happens here, I think, if I'm remembering correctly, sorry, I was confusing it with something else, because I had some discussions on Discord, because I was trying to understand those same things, and I was now confusing myself. So yeah, tests. So I have this separated here in a few directories. Yeah, I wrote some tests for or I didn't write some tests for the NFT side. But there's here a rather long test that does this whole process of deploying the both sides of the NFT contracts, minting a token on StarkNet, bridging it to L1, verifying that all the owners match the expectations and so on, and then bridging it back to L2. So for this, you need that Docker Compose now with the Ganache server, the Ethereum server, and the StarkNet DevNet that we're also running. There's one helper that they include where you can call this load L1 messaging contracts, and you send in the RPC endpoint for your Ethereum contract. Obviously, this is what you should do if you're using a local node for development. In test nets and main nets, that contract is already there. You don't need to do this. Then I do that process where I deploy the L1 contracts, and then the L2 contracts, and finally initializing the L1 again with the address that came from L2. So that three-step process. I just separated this into a few separate functions for readability. Actually, in the meantime, I'm going to run this right here because the test actually takes a bit long, so it may as well run while I'm explaining it. I think I need to... just stop this here. Just to restart the server. Contract here, run tests bridge. This should be it. So, going back to our test, this is actually the test that's going to be running right now, hopefully. So we need to, so we're going to just deal with the token ID 0 for simplicity's sake, and on Solidity side, that ID is 0. On Cairo side, because it uses Win256, it's actually a tuple where both low and high are 0. So this is the only token that we're going to be bridging. So we mint that token for some user on Ethereum side. We assert here that that token ID actually belongs to the user. That's a function that is right below here, this one. It just abstracted a way to keep this whole test a little bit more readable. Then we call the bridge to L1, which is a function that the user himself can ask to do this, or he should ask to do this because he's the owner of the NFT. So I want to transfer this token ID to this L1 user address, and I need to cast these two big ints because the Ethereum addresses in the hardware tester, they're represented as strings. So I first need to cast this to a number, because that's what StarkNet expects, even though it's the same number, just represented in different ways. Now, I should expect that the L2 owner right now is no longer the user, but it's the NFT contract itself, and that works. Actually, the test already executed successfully. And now, going back again to some DevNet helpers, there's one helper here where you can flush the messages and grab everything that's pending, messages going in both directions. And right now, I should expect that messages consumed from L1 are empty because I sent the message, but I didn't actually consume it yet. And there should be one message from L2 that should be, well, that it should include the correct payload, the correct address, correct token ID, and the correct destination address. So then we consume the message on L1, which means that we need to call that bridge from L2 on the L1 side. This is the one that we as the user or the protocol we need to call. This function should work, of course, and now after it runs, the L1 user that we bridge should now be the owner of that same token ID on Ethereum. And then in part two, we just do the reverse, where we bridge the token ID to L2. We again grab the pending messages, except that in this case, messages consumed from L2 should be consumed messages from L1. Yeah, consumed message from L1 should be empty, and there should be one message on L1. Confusing this somewhere. Consumed messages from L1. Oh yeah, because it's from L1. I was confusing the numbers right now. There should be a message from L1, and because it is consumed automatically in this case, we don't need to trigger something on the other side. It should be consumed already. But we still assert that it was sent with the correct arguments and so on. And finally, after all this is done, we expect that the L2 owner is now, once again, the address that we bridged to, so the original owner. And we also expect that on L1 the token has been burned, so there's no longer any owner. Any questions? This, I think, is the more cumbersome part because, I mean, we're dealing with two blockchains at the same time in a single test. And we have to keep all those things in mind and convert things from one type to the other. But honestly, I think it's pretty cool the fact that we can spin StarkNet and Ethereum on a single computer and test this whole process and seeing it actually working. Math is amazing. Any questions? If not, Diogo is looking at me probably because it's time for the coffee break. Yeah. All right. Which is probably the part that you all came here for. So yeah, but actually, so after this, so presentation-wise, this is done. So after the presentation, what I suggest is that, you can hang out here or on the other side. I imagine that some people will have technical problems or depending on how advanced they are on working. You can ask me questions. The Starkware guys will be here as well. You can ask them questions. So I guess feel free to work at your own pace. And yeah, thank you. Oh, most important thing I forgot. The swag is there. Swag is here. Yeah. You weren't here yesterday?
No, I went to the camera.
Okay. Where's my browser? Yeah. So. You have Discord or something? Maybe I can send you. Yeah, Telegram also works. How do I find you? It's your. Oh. All right. And I'm gonna sometime during the afternoon. I hope I'm gonna. So this doesn't have yet this part of the code. I'm gonna move it to the from private repo to here. So.
Oh yeah, sure. Thank you.
All right. I'm very what, sir? Oh, okay.
So let's see.
Are you talking? So let me try to think of. I think I see what you mean. I'm trying to come up with some kind of example. So what are you saying? Something like if I have let's say I'm bridging tokens and there's a swap on the other side, but then in the meantime, so I'm trading tokens here, and then in the meantime someone is yeah. So your protocol needs to take that into account. So for example, one thing I believe, I don't know if it's Jedi swap that does it this way, but there was one protocol that was using this approach where you provide liquidity on L1. So because probably that's where the liquidity is, so it's useful to have it there. That liquidity is it's kind of bridged to L1, so every time there's a checkpoint, the L2 side knows about the liquidity. Trades happen on L2. Yeah, so in this case, this is just state management that you need to do in your own protocol. So of course, you need to take into account that if tokens are being traded on one side, you can't just run things on this side that will break the state. You need to either you need to separate things so that to guarantee that executions here don't mess up whatever happens here. So maybe, for example, to withdraw liquidity, you need to wait for some. Yeah, you need. Let's say I want to withdraw my liquidity from here. That needs to pull the other side to say, hey, liquidity is gonna reduce, and then on the next checkpoint, this is gonna this withdrawal is now in effect, something like that. Yeah. That's pretty much. Yeah. That's essentially it. Yeah, they're actually. I think they're porting to. They're building something on Cairo. I'm not sure if it's a direct port or some integration with the L1 side. Yeah. And because the contracts, so like you saw, when you send messages back and forth, there needs to be a specific target contract on L1 to consume those messages. So yes, you can't just send messages to existing contracts on L1 because unless they're upgradable, because they need to be ready to consume them.
Yeah, if they're upgradable, then I guess you could send them to proxy.
Yeah. If they're upgradable, you can, in theory, send messages right now, and just when they're upgraded, they can consume it. What do you mean, old block?
So like, if I send a message to
L1?
L1 now, and then
2 years later,
2 years later,
you upgrade your contracts.
how does the contract know to like consume messages from
No,
event?
yeah, they're not consumed automatically. So you need to call something to hey, I know there's a message with this specific payload. Let me consume it. Sorry? Well, whatever messages you send, the proof of those messages, so the hash is stored there in a mapping in the StarkNet contract. Yes. So unless it's consumed, it stays there forever. Oh. Are you going to the hackathon? Okay. Yeah, I'm the other way around. I mean, I initially signed up for both, but then there was also the Applied Ziki workshop in the next couple of days. So I applied to that. So I didn't stake for the Ethereum one, and then I didn't get accepted. I'm gonna try to show up there anyway. Yeah, that's usually how these events work. Yeah. Oh, you mean first part of yesterday? Yeah, but did you didn't get an email or what was it?
No, I asked
Oh.
I wasn't sure because the applications are already being closed.
So last week we sent out invites to the accepted ones, but then we're doing it in batches because if these people don't RSVP, then we're inviting people. I think on Wednesday last week it was already full. Yeah, but then people give up, or it wasn't initially in this room. So once we came here, and this is bigger, so we can maybe include some more people.
This is different.
Mm-hmm.
Pretty cool.
Eu conheço isso. Isso não é estranho. Pá, por acaso estava ontem a pensar. O serviço de lavandaria lá no hotel é bué de caro. Diz?
Vai usando.
Não, pá, eu tive que mandar para lá, porque eu literalmente trouxe roupa para 4 ou 5 dias a contar, pá, o hotel há de ter ou há de haver cenas. Então hoje foi mesmo, estava a fazer as contas, pá, eu preciso arranjar t-shirts hoje, porque